I'd like to introduce the idea of compositional formalisms, or formal processes. Traditionally, when we're creating music, people tend to build on the music they've been experiencing and creating before. So they may take some older piece of music and bend it. They can modify it a bit. This is what we're doing when we use a reference for a track. The other thing we might do, we might use two or more musical elements and blend them together. Another thing we might do is we might take some existing musical structure or some musical genre, break them down into the different components and then put them back in a different way. If you think about it, most music education, whether it be classical music or jazz music, whatever, is working from this perspective. We're looking at what people have done in the past and we're trying to learn from that or modify that. But there is one approach which has been used for about 1,000 years, and we can use this to come up with completely different sorts of musical material. It's called Compositional Formalisms. And a formalism or formal process is just a systematic way of organizing or generating some data. So the important thing is it's systematic. And you can use formalisms to transform existing material, which is kind of like what we're doing when we're bending material before, traditional approach. And you can also use them to create completely new material, which is what we're mainly focused on. The general approach, we need to get some formal process from somewhere. So it could be a formula, a game. What we do is we normally raid other disciplines like math and science and geography, astronomy, or wherever, and we use that to generate some data. Then once we've generated a bunch of data values, we map these values to some musical parameter in a consistent way. We could map them to pitch, we could map them to note duration, we could map it to dynamics, we could map it to timbre by having different instruments, we could map it to spatial location. It doesn't matter, we can map it to anything we like, but we do it in a systematic way. What we'll do here is we will get our data, map it to musical parameters, and this will produce a piece of musical material. And we can either use this material as it is or modify it further, use it as a point of departure, and we alter it in whatever way we like. It's a good idea generator. If you want to come up with something new and you can't come up with any ideas that you think just don't sound like everything else, you can use this approach to come up with some new material which you can further modify it, because it's easier to modify something than to create something from scratch just out of the air. So we can classify formalisms into two basic classes. We've got stochastic and deterministic. Each of these can be further subdivided into other subclasses. Let's look at these. Now, stochastic formalisms, they have randomness in them somewhere. That means it's not completely predictable. A lot of people have a funny idea that if it's random, it's not predictable, but that's not true. Random means that there will be an element of unpredictability, but that is not completely unpredictable. We can have a random system that mainly produces low numbers with the occasional high one. We can also control how such a system would work. We can change it so that it mainly produces high notes and just a few low notes. So randomness is not just random, if you know what I mean. And these stochastic processes, random processes, are very good for generating new possibilities. The other type of formalism is the deterministic formalism. Now, in these, if you have the same input, we'll always create the same output. That means they're predictable, and these are good for transformations, but they can also be good for generating possibilities. Let's look at them in more detail. Stochastic formalisms. We have two categories, as I said before. Those where what happened before is important. It makes a significant impact on what we've got, and the previous result affects the next result. We have some examples called random walks and random binary shift registers. We'll have examples of those that we can play with. The other category is when what happened before has no bearing on what we're doing now. History is not important. If we roll a dice, what happened before has no bearing on what we're going to get. If we toss a coin and the previous 7 were heads, we've still got a 50% chance that the next one will be heads or tails. What happened before? Not important. The next result is independent of the past. Now, we are going to play with a bunch of these, and most of them will be probability distributions. Deterministic formalisms. Well, we've been using simple deterministic formalisms for a very long time. Transposition is an example. Inversion, where we flip the intervals upside down. Playing it backwards, which is what retrograde is. Augmenting intervals. They're all examples of deterministic systems. So there are more complex deterministic systems available, and they're very good at generating new material. There's these things called finite state automata, chaotic systems such as fractals and the logistic function, which we will be playing with. Other things like polynomial generators, they're basically just mathematical functions, and cyclic generators, where we have a couple of low frequency oscillators that are running at a constant frequency. They will create repetitive behavior. You can always predict what's going to happen. So this is what we're going to be looking at to be able to create new musical possibilities.